Hey guys, thanks for tuning in. In this video, I'm going to talk about plotting tangent planes. I'll talk about how to do this both parametrically and how to get the xyz equation for a tangent plane. But before we jump into tangent planes, it might make sense to talk about the tangent line to a curve and then kind of build up to three-dimensional space. So let's start with just some p of t equals x of t, y of t. That's a parametrically defined curve. So this little star-shaped looking thing that I came up with. So let's say that we want to plot a tangent line to this curve at some given point, and let's say we want to do so parametrically. Well, you guys know the parametric equation for a line. It's L of t is equal to p plus tv, some starting point plus multiples of some slope vector. Well, I could take this equation and try to adapt it to this whole tangent line idea to a curve. So we have our curve p of t, and we want to have a tangent line that is intersecting the curve at some t equals a. So honestly, I could just take this equation that you already know pretty well, and as long as I could find a starting point, and as long as I could find a slope vector, I'm good to go. Well, our starting point should probably be p of a, the point of tangency, and then my tangent vector, I could find that by computing the derivative of p, so p prime of t evaluated at a. So here it is. My tangent line is L of t equals p of a plus t times p prime of a, where p of a is my point of tangency and p prime at a is my slope vector. And I could show you that it works, so I ran this through Mathematica, and you could see the formula right there, and I picked a point of tangency that I came up with here, and we have a tangent line to our star shape at some particular t value that I picked out. All right, so at this point you might be wondering, okay, that's kind of cool looking, looks very familiar from my Calc BC class because I already knew how to plot a tangent line to a curve, but I used to do it using xy equations, not using parametric equations. So how does this all tie together? So let me show you. Let's say we take this formula we just came up with, and let's suppose that we have a y equals f of x like you would have seen in your previous course. Well, we can, if a y equals f of x curve we can always be parameterized for free. And that free parameterization is p of x is equal to x comma f of x. You could do that to any y equals f of x curve and that'll parameterize it. So let's take that and run it through that equation we just came up with. So here's what we came up with in the previous part. L of t is equal to p of a plus t times p prime at a starting point plus multiples of some slope vector. Well, p of a is a comma f of a, that's my point of tangency. And then p prime at a, well, I guess I can compute this derivative here. The derivative of x with respect to x is 1, and the derivative of f with respect to x is f prime at x, and then we evaluated that at a, so f prime at a there. And then I have two ordered pairs being added together. You know what, I can just combine that all into one ordered pair. So I have a plus t, comma, f of a plus t times f prime at a. Okay, so it's starting to look a little familiar here. Now remember, this ordered pair is an x-coordinate, comma, a y-coordinate. So I'm going to take out this x-coordinate and say it equals x, because it's our x-coordinate. So x equals a plus t. It's just the x-coordinate from our ordered pair. We can do the same thing for the y-coordinate. So y equals this gobbledygook that we have right here. So y equals f of a plus t times f prime at a. Oh, wait a minute. If x is equal to a plus t, I can solve that for t and see that t equals x minus a. Then I could substitute this t equals x minus a into my equation for y, and I get y equals f at a plus f prime at a times x minus a. Oh, look at that. That's our really familiar equation for a tangent line from our previous calculus course. This is just point slope form. Y minus y1 equals m times x minus x1, where our x1, y1 is our point of tangency, a comma f of a, and our slope, m, is f prime at a. Oh, so we just rederived the formula that we knew from our previous calculus course. Essentially, we deparameterized this tangent line equation for a curve y equals f of x, and you can see that we get what we previously knew from our last course. I could show you that this works, and the way I'll show you that it works is I'm going to come up with some f of x that I just made up and a point of tangency that I made up, and let me do it using both formulas. So here is the traditional Calc BC way of doing this. So I've got my f of x and my tangent line using last year's formula. Oh, it looks kind of cool. So here's my curve, here's my tangent line at some given point of tangency. A equals 1.75 is what I had picked, just because I kind of like the angle on it there. Let's try it again. So now look at this. I've parametrically defined my curve, and the parameterization is this free parameterization that we get. I wrote it as P of t here. You can also write it as P of x, but I wanted to accentuate the t's here because we kind of think t when we're plotting parametrically, and we think x's and y's when we're plotting more traditionally using Cartesian coordinates the old-fashioned way. Anyway, so I have my P of t equals t comma, my f of x, but evaluated at, t comma f of t essentially. Anyway, when you plot it, oh my gosh, look at this. They are the exact same plot. Both methods produce the same result. Now we're going to repeat this process again, but we're going to try to do it for a parametrically defined surface. Now this looks pretty similar to what we saw above, but now we have P of s comma t, so two parameters, give us some x of st, y of st, z of st. Basically, we have a surface living in three-dimensional space because we could see an x-coordinate, a y-coordinate, and a z-coordinate. And now we depend on two parameters, not just one parameter, because we have a surface. So again, our task is to plot a tangent plane to this surface at some given point. And you might want to remember back to how to define a plane parametrically. Well, it's very similar to the parameterization for a line. It's a starting point plus multiples of one slope vector plus multiples of another slope vector. And if we have two linearly independent slope vectors there, we get a plane. So again, we want to try to adapt this kind of general equation for a plane specifically to a tangent plane to a surface. A tangent plane to our surface P of st for, an s and t value for a point of tangency a comma b. Well, if we kind of follow the same recipe as above, if we could just figure out the necessary parts for our plane, we're done. We need a starting point, and we need two slope vectors. Well, the starting point's easy. We're going to use our point of tangency again. And so our point of tangency is the equation for the surface evaluated at our point of tangency a comma b. Okay. And then our tangent vectors, well, in the previous example, we computed a derivative, right? We had, P of t and we computed P prime of t. Well, that prime notation is only really useful when you're doing single variable calculus, because the prime notation of the derivative of P of t equals P prime of t, that prime is implying that the derivative is with respect to t. But now that we have multiple variables, we have two parameters, s and t, and we could take a derivative with respect to either one, we need a new notation here. So I can't write P prime at a comma b, but I can write the partial derivative of P with respect to s evaluated at a comma b, and the partial derivative of P with respect to t evaluated at a comma b. This is kind of our analog of prime notation, but this subscript here is telling us what variable we're going to be taking our derivative with respect to. All right, so let's look at this equation here. So I've got the equation for my tangent plane is equal to, a starting point, our point of tangency, plus it's our first slope vector, the partial derivative of P with respect to s evaluated at a comma b times s, plus our second slope vector, the partial derivative of P with respect to t evaluated at a comma b. Oh, everything lines up. If you line up the equation of the parameterization of a plane with this tangent plane equation, everything matches. Point, slope vector, another slope vector. All right, well, let me try crunching some numbers. So I'm going to make up a surface here. I just made up some surface that I thought plotted out nicely. I made up some point of tangency, and let's see if we could take the equation for this surface and this point of tangency and find the equation for the tangent plane to our surface at the given point. Okay, well, I have to do some number crunching now, right? So I have to take the equation for my surface and plug in my point of tangency. So I'm going to take a equals 1 and b equals pi over 6 and plug it into my P of st. Okay, so s cosine of t evaluated at 1 comma pi over 6, that's 1 times cosine of pi over 6. Same thing here, s times the sine of t, that's 1 times the sine of pi over 6. And then this one's nice and easy to evaluate. 4 minus s squared is just 4 minus 1 squared. Okay, I know my unit circle, so I know that it comes out to root 3 over 2, comma 1/2, comma 3. All right, that's just our point of tangency. That's just the point where the surface and the tangent plane are going to end up intersecting, or at least the first time that they're guaranteed to intersect. And then we also need some partial derivatives. These are our slope vectors. So you guys could see how I compute these partial derivatives. So first I do it in general, just in terms of s's and t's, and then after that I'll go ahead and plug numbers in. All right, so my surface is s cosine t, comma s sine t, comma 4 minus s squared. So I'm going to take the partial derivative of this equation with respect to s here. Okay, well, what's the derivative of s cosine t with respect to s? It's cosine t. Same thing for the next one, I get sine t. And then what's the derivative of 4 minus s squared with respect to s? I'm going to get negative 2s. Evaluate that at s equals 1 and t equals pi over 6, and I get this vector right here. Do the same thing for t now. So we repeat the same process, but we take the partial derivatives of each of these three parts of our ordered triple with respect to t. So what's the partial derivative of s cosine t with respect to t? Well, that's negative s sine t. Similar idea here, the partial derivative of s sine t with respect to t is s cosine t. And here's a cool one, 4 minus s squared has no t's in it. So it's constant relative to t, so its partial derivative with respect to t is 0. And then we go ahead and do some plugging in here, catching typos as I go, which is kind of nice that I'm seeing those as we're going here, rather than having to catch them after the video's over. Anyway, we can then put this all together just by plugging into this, general equation for a tangent plane, and I did this calculation by hand. It took me a few minutes to do all the number crunching. Mathematica makes really quick work of this type of problem. So Mathematica can compute partial derivatives faster than I can, and it can evaluate functions way faster than I can as well. So here's our tangent plane to our parametrically defined surface. How did we do it? Well, we had a starting point, and we had two direction vectors, two slope vectors, and that was enough to define our tangent plane. You can see, nice and tangent to our surface. Okay, again, you might say, okay, now I know how to do this parametrically. What if I have a more traditional equation in the form z equals f of xy? How would I find the xyz equation of my tangent plane? And this completely mirrors what I showed you before. So it's going to be the same algebraic process, just with these, multivariable formulas rather than the single variable formulas I showed you before. So our surface is defined as z equals f of xy, so we can parameterize it for free as x comma y comma f of xy. You can always do this. If you have any z equals f of xy, you get a free parameterization by making x your first parameter, comma y your second parameter, comma f of xy your z coordinate of your ordered triple here. Now we have this beautiful formula from the previous text cell, so let's use it. Let's see, so I'm going to have to compute some partial derivatives again. But wait a minute. My parameterization is x comma y comma f of xy. So what's the partial derivative of that with respect to x? Well, the partial derivative of x with respect to x is 1. The partial derivative of y with respect to x is 0. And then the partial derivative of f with respect to x is, well, you write a little subscript here, so f subscript x, x comma y. That just means the partial derivative of f with respect to x evaluated at x comma y. Repeat the same process to get the partial derivative of p with respect to y. You get 0 comma 1 comma the partial derivative of f with respect to y evaluated at x comma y. All right, now to plug into this formula, I'm going to have to plug in a's and b's for my x's and y's. So my tangent plane here is going to be L of st is equal to my point of tangency plus my partial derivative with respect to x multiplied by s plus my partial derivative with respect to y multiplied by t. Let's plug in all the stuff I just found. And then if we expand this out, Basically, if we have 3 ordered triples here. If I combine everything to have just one big ordered triple, my x value becomes a plus t, my y value becomes b plus s, and then my z value, fairly complicated there, we'll unpack that in a second. So let me write those all out. My x coordinate was a plus t, my y coordinate was b plus s, and my z coordinate, fairly complicated, but also the most useful part of this ordered triple, so we'll come back to that. We'll rearrange some terms just like we did with the tangent line example. So if x is equal to a plus t, we could rewrite that as t equals x minus a. Same thing for s. And then we'll do some plugging in. This is the process of deparametrizing this curve or this surface. So I'm deparametrizing here. I'm getting rid of the t's and s's by plugging in. So I'm going to replace this t with x minus a, this s with y minus b. I did a little bit of mixing up x's and s's and t's here by accident, by the way. Quick fix, though. So really fast, if I'm going to fix this up, did a little bit of swapping here. My apologies. Almost done. Might have been better to just leave the typo in there because you guys probably get the idea. But the assignment of t's and s's is not really the important part, right? The important part is that we're doing some substitution here. So now I rewrote it as s equals x minus a and t equals y minus b. But the important thing is I'm replacing this s with x minus a. I'm replacing this t right here with y minus b. And what do you get? This beautiful equation for a tangent plane. It's nice and friendly looking because it looks very reminiscent of the equation for a tangent line. It almost looks like a, kind of like a point slope form here for the equation for a tangent plane. So I could rewrite this as z minus f of ab equals partial derivative of f with respect to x, evaluated at a comma b times x minus a, and then partial derivative of f with respect to y, evaluated at a comma b times y minus b. Anyway, let me show you that this works and that it doesn't matter whether you do this parametrically or whether you do this with xyz equations, you're going to get the same tangent plane. So I'm going to take f of xy equals this equation that I came up with at a point of tangency 1 comma negative 1. So the first time I did this with a parameterization here. So you could see that I'm doing the parameterization of f, and I'm using the formula that we had parametrically, and we get this cool looking surface with a tangent plane. And then I'm repeating the same exact process again, but now I'm plotting my surface non-parametrically, just as an xy equation, or xyz equation, whatever. And then I'm using this xy equation for the tangent plane as well. Same picture, compare the two, look at that. I don't care if you do it parametrically or using xyz equations, you are going to get the exact same result, which is kind of cool. Now, one thing I would say is Mathematica can do these really fast, but you should be able to do these by hand. So, for a quiz, for a midterm, whatever, I think you need to be able to do a little bit of number crunching by hand for this course. So let me take my f of xy equals 3 e to the negative x squared minus y squared over 8 and my point of tangency at 1 comma negative 1. And let's just see if we can do some number crunching without the computer doing the work for us. So, for example, one skill that you'll need to develop is taking partial derivatives. So here's the partial derivative of my function with respect to x. Just a little bit of chain rule here. And the thing that makes it interesting is this negative x squared minus y squared over 8. This portion of the function, when I take the partial derivative with respect to x, this y term is constant relative to x. So when we're using chain rule here, the derivative of negative x squared minus y squared over 8, its partial derivative with respect to x, we're going to end up just with an x term coming out. So I have negative 3x over 4. The 3 was a coefficient that was already there, and then a negative x over 4 comes out of this, this exponent when we do chain rule. And then you know how e to the x works. The derivative of e to the u is going to be du dx times e to the u. So basically, you could see that they still have my e to the u there. Now I can evaluate this at 1 comma negative 1 because that's where my point of tangency is going to be, and I get my little my partial derivative of f with respect to x evaluated at 1 comma negative 1 right here. So just plug in all x's become 1s and all y's become negative 1s, good to go. All right, moving on, we could do the same thing for the partial derivative of f with respect to y. Notice that I'm doing this with x's and y's first, and then I'm evaluating at numerical values after I've gotten my equation. So this kind of mirrors what I just showed you, so I'm not really going to go through the details here. Same equation, except for it has a y in its coefficient instead of an x. And then we're evaluating at 1 comma negative 1. Well, the only thing that kind of changes here is we are plugging negative 1 in for this y value, so a negative times a negative is going to make a positive result, but that's my next coefficient for my tangent plane. And then finally, I do need to find the z value when I plug in f of 1 comma negative 1, and here it is. So these are the three things that I need for my equation, right? I need this z value, I need this first coefficient, and I need this second coefficient, and I could plug it all in. And here's the equation for my xyz equation for my tangent plane to this surface. We can easily check our work in Mathematica. So I ran this through the computer and had it spit out a result, and I could see that everything matches here. Now, this constant, you could have it on the left or right side of the equation. Up here, I have it on the left side. Mathematica has it on the right side, but it, if you go term by term here, you could see you get the exact same equation, maybe written slightly differently, but it's the same equation. All right, so that's how to do this problem by hand. And let me summarize real quickly. There's 4 interesting formulas in this video. The formula for a tangent line to a parametrically defined curve, the formula for a tangent line to a curve y equals f of x, so an xy equation, and then stepping up a dimension, a tangent plane to a parametrically defined surface, and here's that tangent line or tangent plane defined parametrically, and then a tangent plane to a surface that's given by an equation z equals f of xy, so this is an xyz equation. All right, guys, I hope you enjoyed this video. Remember, I did share this Mathematica notebook on our Schoology page, so you can access any of this material later. Enjoy, and I'll see you guys soon.